Okay, so keep working with adding and subtracting of radicals. We know we need like radicals to do so, so the indexes have to match, the radicands have to match, and then we combine the coefficients. So this one's a little more involved, but it's under the basic premise. We could add variables underneath. We know that radicands have to match, but the indexes also have to match, which indexes do, so it's a good start. So as you go through, if you see that you've done a process and something has the same numbers, don't repeat that process. What I mean is, if you go through and break down s to the fifth in one of the various ways that we've shown it, we can just then apply that type of answer to the r, but just change what we're doing to the r. Okay? Look at this. So remember, we could think of this as, we think of the product rule, break it up. We could think of it as square root of 4, square root of r to the 7th, square root of s to the 5th, if you need to visualize that. Well, square root of 4 I know is 2. Okay? So, as we go through, and that's supposed to be a plus. As I go through, I have r to the 7th. Well, I know I can break that down. R squared times r squared times r squared. We're using the product rule in reverse. I could use the power rule. But remember we had this. So this is the r. We're taking 7, the power, divided by the index, which we know is 2. 2 goes into 7 3 times. So I know I'm going to have an r cubed outside. 3 times 2 is 6. 7 minus 6 is 1. I know I'm going to have an r inside. Well, if I repeat for the s, that idea, we're going to have 2 dividing into 5. Well, 2 goes into 5 2 times. That tells me I have an s squared. Remember, this number here is the power on the variable outside. 2 times 2 is 4. So we subtract 4 from 5, we get 1. So we have an s inside. These numbers represent the power on the variable inside. So as I go through, as I talked about, we have an r to the 5th. So we've got, that's similar to s to the 5th. I don't need to do this again for the r. Just realize that I'm going to have the 2rs already, but then I'm going to bring out an r squared. Okay. Unfortunately, we didn't have another s with an s cubed, but we could think of that in this s squared times s. So I'm going to take out an s. So I have another s here. What gets left behind will be this r inside and this s. Well, if you clean that up, r to the 1st times r squared, we have 2r cubed. S times s is s squared times r to the s. So we rewrote that. Well, 2r cubed s squared, square root of rs, 2r cubed s squared rs. The reason I want to give this to you, not only do the indexes have to match, and the radicands for these to be like radicals, if I want to go through and combine it into one item, we have to fall on that old information we already did. If you take away the r to the s, what we have to ask ourselves, are these like expressions? 2r cubed s squared, 2r cubed s squared. Remember, the idea of a like term is that they have the same variable and the same exponents on those variables, and then we combine their coefficients. So if this was just an s, it wouldn't match with what we had here. And we wouldn't be able to combine them in the sense of one item. We'll see a process down the line. But these match also here. So 2 plus 2 is 4. Now oftentimes what I see is students will lose information. This is 2, say this represents apples. This represents apples. Well, 2 apples, that's 4 apples. It doesn't change this. So this is still r cubed s squared, square root of rs. If that had been minus, 2 minus 2 would be 0. 0 times all that would be 0. Okay? This information out front, that's old information. That's 090 information. Those have to be the same for us to combine the numbers. Okay? grab my sheet here. You know what, we'll go to the next clip.